So yeah, hi everybody. There was some malfunction in my computer, so I had to. Sorry for the delay. I joined earlier, but I'm recording it a bit late. But that was no problem. As usual, I'm here to give you my live session for the week, and this week we'll be looking at heat flux. And as usual, we'll wait for another 10 minutes or so to see if there are any more people who will be joining us. And yeah. Alright, then let's start. Um, yeah. So, as I said, we are going to look at heat transfer today. There are three types of heat transfer. One is conduction, convection, and radiation. You should know this by now. This is high school physics, and actually, in the course, you would be like how you have learned about diffusive flux. You would also be learning about the conductive heat flux, and which is given by Qx, which is analogous to fixed first law of diffusion, and basically the heat flux is related to the rate of change of temperature with respect to x, and k is the conductivity of a specific compound, a specific substance, and depending upon the conductivity, the heat transfer might be faster or slower, and that is an intrinsic property of the substance. So I don't want to dwell on this further because this is similar to diffusive heat flux, and I'm sure you by this time you should have had a good grasp of that. So this is the equation in one dimension, and this is the equation in three dimension. I'm sure you understand these notations as well. So let's now think about this, and I have a question for you guys. So refrigeration. So basically, in your home, you all um, some of us have refrigerator in our homes, and what is the type of heat transfer that happens in a refrigerator? And that's the first question, first part of the question. And the second question is there is something called as forced convection and free convection. Forced convection is the heat flux because of the flow of a fluid, and forced convection is because of the flow of a fluid uh, due to a driving force like a pump or a compressor or some other instrument. And free convection is due to the um, change in the density of the um, fluid that we are dealing with due to various factors, like phase change or temperature change or something like that. Now think about this and let me know, please, in terms of the second part of the question. For free convection, what type of fluid is preferred and why? Let's say if you need to select a fluid, you have a liquid fluid and a gaseous fluid, and both can do the job for you. Which one would you prefer and why? So I'll give you a minute to think about the answers for these questions, uh, these two parts of the same question, and I'll give you the answer after that right away. All right, so I think most of you would have guessed the first part of the question because Um, Refrigeration is because of the refrigerant that's present in your compressor, and that's a fluid, and because of the flow of the fluid, there is a heat transfer, and it's because of convection. And for the second part of the question, given that you have two choices, one a liquid and one a gas, and you would want to have free convection, and which one would you prefer? The answer is you should prefer the gas as a fluid, because gas is a compressible fluid, whereas liquids are typically incompressible. And the density differences that can happen in a gaseous fluid is much more higher than that than that which can happen in a liquid. And thereby, if you are going to choose for free convection, which typically happens because of change in density, you typically will choose a fluid which will have the which has a higher propensity to change its density, or a compressible fluid, in other words, and that is why you should choose a gaseous fluid. So that's the answer for these questions. Very simple. And now I would in this course you would be reading more about conduction, and later on about convection also. But radiation was just touched upon. There was Stefan's law, and about radiation, there is a very interesting concept, or very interesting phenomenon, that was observed in the early 1900s, which was called as the ultraviolet catastrophe. So basically, a black body, you should know that a black body is a substance that emits radiation, and it's what a black body does, a thermal equilibrium, is that at different temperatures it has different radiation intensities at a given wavelength. So if you see this graph, this is the wavelength, and this is the spectral radiance. In other words, so here the radiance is lower than the radiance here. It's apparent, right? This is at 3000 Kelvin for, let's say, substance X. So sorry, a black body X. So this black body was, if this black body was heated to a temperature of 3000 Kelvin, it was observed that you know the experimentally observed that this black body will emit uh, this amount of um, radiance at this wavelength, and it will emit this amount of wavelength. I mean, sorry, this amount of energy in terms of radiation at this wavelength. So at wavelength 1, the irradiance at that wavelength 1, at the wavelength of 1 micrometer, the radiance is higher than that in 3 micrometers. So that is the spectral radiance. Spectral radiance is a function of the wavelength of the emission of the radiation. It's very it's quite simple, actually. So this was governed, or this phenomenon was explained by um, the Rayleigh-Jeans law, which you see it here. So basically, BT of lambda is the spectral irradiance. So it is. I'm not going to go into these terms. You can easily understand these terms by now. It's basically a function of the inverse of the fourth power of the wavelength. So as per this law, um, the spectral radiance at a given wavelength is directly or inversely proportional to the fourth power of the wavelength. Now, first of all, let's understand one thing. I told you about spectral radiance. Let me go to the next slide. How to find the spectral radiance at a given temperature from the given graph. So basically, what I'm asking is, at a given temperature, there are different types of the different temperatures. This black body is heated, one at 3000 Kelvin, one at 4000 Kelvin, and one at 5000 Kelvin. So to find out the total spectral radiance of the black body, what would you do? Um, irrespective of the total spectral radiance at all given wavelengths. How will you find it out at a given temperature? The answer is very simple. It's very, very simple. um, I would suggest you think about it for a minute and I'll give you the answer. Remember this graph is at let's say at I'm repeating this at 3 micrometer wavelength. This is the amount of irradiance, and at 1 micrometer of wavelength, this is the amount of radiance. Now what I am asking is, how would you find out the spectral radiance at a given temperature for all the wavelengths? The answer is simple, right? It's area under the curve, right? So you add up the spectral irradiance at the wavelength 3, and then you add up the spectral irradiance at the point 2.5, at the wavelength of 2.5, same as 2, 1.5, etc., 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 which is basically integration, which is the area under the curve, in other words. Now the problem with this Rayleigh-Jeans law was derived from classical theory, classical mechanics. And what the problem is this, right? So when the wavelength of the black body, the wavelength of the light that is emitted by the black body tends to zero, or the energy, like when you heat the when you heat the black body to a higher temperature, the energy of the emitted light will also be higher, because obviously, right? So according to this law, when you increase the temperature progressively, the wavelength uh, will start to decrease, or the energy of the emitted light will start to increase. And as this wavelength tends to zero, which means as the temperature of the system increases, as the energy of the emitted uh, light increases, or in other words, the wavelength of the emitted light decreases, the spectral irradiance goes to infinity. So Rayleigh-Jeans law was able to explain experimental results only up to a certain temperature and for up to a certain wavelength. It was not able to explain itself, for a certain temperature. So it was not able to explain the phenomenon, the experimental phenomenon, that is all these colored graphs, right? Red, green, and blue. These are experimentally derived results, and uh, after a certain point of time, after a certain threshold of temperature, it was not able to explain this phenomenon. And so what happened? What happened was something phenomenal. The physicist Max Planck, he came up with a uh, brilliant twist to explain this experimentally obtained results and the flaw in the classical theory. What he said was, the light cannot be viewed as a continuous medium, or in other words, light itself can be divided into subsets of energy packets, subsets of packets of energy, which are also called as quanta. So when he introduced this, he had no idea of you know uh, quantum mechanics, or quantum mechanics was uh, not a subject then. No, it was not even there. So what he did was, he just assumed that wavelength, I mean, the emitted light is not a continuous source, but it is made up of packets of energy or quanta of energy. And the probability of finding or let's put it this way, um, when a black body emits light, it emits an ensemble of photons, correct? So it basically emits many millions of photons or something like that. Now um, the pro the to explain this intuitively. Okay. Um, the expected value of of a photon of light, of the energy of a photon of light, which is given by E, is a function of the energy of the photon and the probability of finding that photon of that given energy. I'm kind of not explaining it to you intuitively. So now let's go back to the ensemble of photons that we are talking about. So whenever you talk about an ensemble, it's a distribution, correct? And the probability that you find a photon of a given energy, h nu, which is nu is c by lambda. So the probability that you will find uh, a a photon of energy hc by lambda can be roughly correlated with this term 1 by e power hc by lambda kt minus 1. And now this e power hc by lambda kt minus 1 is you know um, you should be familiar with this term. This is kind of looking like Boltzmann statistics, correct? So this is a distribution called as Einstein-Bose distribution. And so the in other words, a quanta of photon at a given energy will exist depending upon this probability. And now, if you apply the same idea here, when lambda tends to 0, e power hc by lambda, this becomes infinity, the whole denominator becomes infinity, and the prob and the and because of that, the probability of finding a photon in that high energy photon in that ensemble of photon decreases uh, with its with an increase in energy. So given an ensemble of photons, the probability of finding a photon of increasing energy decreases exponentially. Yeah, that's what this says intuitively. So this was the foundation for the field of quantum mechanics, this quantization of light. And Einstein took this further, and he explained it as he gave the um, word photons to it, and you know what he did? He was awarded the Nobel Prize for the photoelectric effect. But Dr. Planck was the person who brought this mathematical twist of a quanta of photons, and that's about this. That's about that. So, if you have not understood this thing properly, again, I'm going to repeat this once more. A black body emitting light will emit light, and that light will have an ensemble of photons in it. And this ensemble of photons will have a distribution. And the probability of finding a photon of a given energy will decrease with an increase in the energy of the photon. And this is given by this equation. I'm not going into the derivation of all these equations. If you want, you can take this concept from here, and if you're interested, you can go and see it. But this this was able to explain the phenomenon of ultraviolet catastrophe. Now let's answer some questions on this. So let's say that what is the thermodynamic problem from the classical point of view? Let's assume that Rayleigh-Jean's law was true. What would be the problem here in thermodynamic terms? It's a very simple question. I'm going to give you 30 seconds to think about it. Yeah. So if this were true, at 3000 Kelvin, when you heat a black body at 3000 Kelvin, you will get a finite amount of spectral radiance. As I said, the area under the curve. When you do it for 4000 Kelvin, you will get a finite spectral radiance, but the spectral radiance will be higher because the temperature is higher. But if you heat it at 5000 Kelvin, according to classical theory, you will get infinite amount of energy. So that is thermodynamically not possible, right? So that was a flaw in terms of thermodynamics. Now the problem 4 or question 4. Let's say if the ultraviolet catastrophe was true, if the classical view of this equation was true, what would happen to life on Earth if the predictions of the classical theory were true? Let's assume that if you heat a black body at a temperature of 5000, more than 5000 Kelvin, you're going to get infinite energy. What would happen to life on Earth? Again, the answer is simple. If that is the case, the temperature of the sun is around 5776 Kelvin, and assuming that it's a black body at thermal equilibrium, it will start to emit intensities, an infinite amount of its spectral radiance will be infinite, and as the wavelength of the as you go to smaller wavelengths, from visible into the UV, the spectral intensity will be, tending to infinity. In other words, there will be a lot more UV rays, infinite. This is a hypothetical, this is a thought experiment. So for, let's say, the amount of the quantity of UV rays that we receive now will be that we receive on Earth will be much higher if the classical theory was true. What will this do to life on Earth? We don't know actually. We might think that we will die. We will die because we cannot. Our body is not, or any organism's body is not. So on this earth as of now is not conducive to take up that much of ultraviolet and light. Your genes will mutate like crazy, and much of us will die, but we don't know what will happen to life, because all those mutations could lead to a totally different uh, set of fundamental tenets of life that could result in a totally different path evolution that evolution might take. So for people who thought that life on earth will end and stuff like that, we will end. We will die. Most of us will die, but the people who survive, they might produce offsprings who might live in a totally different environment than what we have today. Now, when you now looking at the assignment questions, the assignment questions for the heat flux is it's kind of, it's okay. It's not a big deal actually. So some of the questions in the assignment, you need to derive certain things. So I would like to focus on a particular concept that was that's actually explained in one of the lectures, the temperature profile in a tissue. Because if you understand this, you will be able to answer questions that are given in the assignment. I'm not going to discuss the questions in the assignment, but I'm going to discuss this in a very short way, because uh, Dr. GK sir has already have Dr. GK Suresh Kumar has already discussed this at length in his lectures in a beautiful way, so you can go and see it. But I'm just going to give you the gist of it, and so that you'll be able to solve the assignment questions. Now, if you have come to this, if you have read his book and or listened to his lectures, the assumptions are quite straightforward. So basically, what they're asking is that let's assume that there is a tissue, a cylindrical tissue. We are assuming that the tissue is cylindrical, and the surface temperature of the tissue is well maintained. It's at homeostasis, and there is no fluid flow inside the tissue, and there is no heat flux in the axial directions. Now I think you should be familiar with what is axial and what is radial. If you are not, please Google it. Radial is yeah, I don't want to spend much more time on that. Google it. Now, the third assumption is a steady state assumption. There is no change in the temperature profile inside the tissue with respect to time, and there is also metabolic heat that's generated in the system in the terms of and it's denoted by Qm dot. So I would suggest you look at you listen to his lecture and read his book. I'm just giving you the gist, and you will be much more clear. These things will be much more clearer. I mean, I think these are straightforward. I don't think you need any more um, explanation for these things, but please do read up on his book and listen to his lectures. It's good. Now, what is this? This is basically, this is this equation. I'm sure you know. This is basically what we are saying is that we are the equation of energy. We are taking the cylindrical version of it, and this is the whole equation, and I'm going to explain it to you why these things are zero. So we assume steady state, there is no rate of change of temperature with respect to time, so this goes to zero. And now the key is that we have assumed that there is no fluid flow inside the tissue, correct? So basically every velocity terms will get cancelled. So Vr is cancelled, V naught V theta is cancelled, Vz is cancelled, and any other term which contains theta or any velocity profile, they're all cancelled. So it's given here. There is only the metabolic heat that's generated inside the tissue, and if there is any other work that is done by the tissue to the surroundings or on by the surroundings on the tissue, that we are not assuming any of that. So the other type of work is also zero. Now this yields equation 1. Um, and from equation 1, assuming certain boundary condition, you go to equation 2. So basically this gives you a temperature, this gives you the means of finding out the temperature at a point x inside the tissue, and Ts is the surface temperature. The surface temperature, as we said, is that it's maintained at it's at homeostasis, typically at 37 degrees Celsius, and all the other terms are fairly they're self-explanatory. K is the conductivity, and so basically the temperature. I told you the temperature at a point x, right? Leave that out. Temperature at a point r, small r. Okay. The capital R is the radius of the sphere, The small r is the point of is the point at which you are trying to find out the temperature inside the tissue. So at any given point inside the tissue, you will be able to find out the temperature using this equation and all these other all these other constants that are given. So basically, when you find, say, read a question in your assignments that would require you to do certain derivations or something like that, it should be similar to this. That's a clue. And now there is also, now that's one thing. Now, the second thing is, there is also, when there is a surface area, there is always heat dissipation, right? So the areal heat dissipation across the surface of the tissue is given by the area into the flux, which is basically 2 pi RL into the heat flux when R equal to R. The small r is equal to capital R. So if you just substitute you know QR, which is equal to minus k into dt by dr at r equal to r, you get this equation. For more details, I would suggest you to read the lecture, listen to the lecture. And now we would like to find out what is the temperature at the center of the tissue, at a point of r equal to 0, small r equal to 0. When you substitute small r equal to 0 here, this term becomes 1, and basically the Tmax is Ts plus Qm dot into r squared by 4k. This is the maximum temperature that can be found inside this tissue sample. So if you look at the lecture and if you look at the book, there is a beautiful drawing which basically states that um, the temperature profile at the center of the tissue, the temperature at the center of the tissue is maximum, and it is parabolic in nature. So basically, from whichever side you come in a radial direction, either from the upper side or the lower side, you are going to have a similar temperature profile, and that's how it is. And if you look at the lectures, you would also understand that he the professor has given certain numbers for these certain values for these terms, and he has come to a conclusion as to what to expect of the temperature at the center of a tissue for a typical tissue. So I would let you to go through the book or read the lecture for that. Look at the lecture for that. Listen to the lecture for that. Now I have a question. A very interesting question, I think. A laboratory grows two tissues of the same organism, one wild type and the other exhibiting type 2 diabetes. Type 2 diabetes is the presence of high sugar in the bloodstream. In other words, the cells that are present in in the tissue, they are not able to absorb the glucose from the blood or the media. This is a tissue culture room, right? So basically, if a type 2 diabetes culture is grown, and assuming that you know uh, not assuming, if that is grown, the cells won't be able to take in glucose efficiently, and thereby will result in it won't be able to take in glucose efficiently. Okay, so this is a thought experiment again. There are two tissues. One is a wild type tissue which takes in glucose nicely, and other exhibiting type 2 diabetes which doesn't take in glucose nicely. High sugar in the bloodstream or high sugar in the media. Hypothetically speaking, will there be any difference in the temperature profile of the two systems? If so, why? That is the question. I would leave you to think about this and look at this whole thing and these assumptions and this equation first for maybe 5 minutes or something like that, and after that I will give you the answer, 5 to 10 minutes, and then I'll give you the answers. And assuming Let me just check if anybody has joined today. Nope, only me. So in the off chance that when you see this lecture, I'm going to give you 5 to 10 minutes to crack this. And the clue is that it's the answer is embedded in the assumptions and in this equation. Knock yourselves out. Any idea? So the answer is simple, right? I mean, it's not. It's logical, right? So so basically, if a cell is not able to take in sugar because of insulin, sugar means glucose here in this case, it will not be able to perform its metabolic activities well. And if you see here, the heat generated in the tissue is basically a function of the metabolism of the cell. And the more the metabolism is active, more metabolically active the cell is, the more metabolic heat that will be generated. So if you look at the temperature profile of the two tissues, uh, most in theoretically they are both of their the wild type tissue should have a higher temperature profile at T equal to, or at R equal to 0, when compared to that of the tissue that is having a um, uh, type 2 diabetes kind of a condition, or it's been engineered like that. So in other words, the parabola that I was talking about, and that you'll see in the lectures, and it's also there in the book, will be higher for the wild type tissue when compared with that of the tissue with type 2 diabetes. So yeah, that's about that. And I'm going to wait for actually it's already time, right? So alright then guys, I hope you watch this video, and I hope you enjoy this video. Alright then, thank you. Bye bye.